So a precipitation reaction is one in which a precipitate forms. A precipitate is a solid. And just like snow is precipitation, rain is precipitation. It's something that falls down in the solution. So hard water, which is what comes out of our faucets, contains dissolved ions, calcium ions, magnesium ions. The hardness of water depends on the concentrations of these dissolved ions. So if the water is soft, it may still have some ions dissolved, but very few compared to hard water. And you can have super hard water, like out at my mother-in-law's place out in the country where she has a well, and her water, it'll almost stand up by itself, it's so hard. It's just dissolved calcium and magnesium ions. So these react with soap to form this gray curd-like substance. That's kind of the slimy stuff, also known as bathtub ring. Here on this ugly bathtub, you can see this white scummy stuff. Now there are hard water deposits that get on your fixtures, and then there's the soap scum, the bathtub ring, which is this kind of slimy stuff, which you can scrub off. Then there's the hard water deposits that seem to be like pretty much almost permanent. And the lights are possessed. We were too quiet. Okay. Yeah, it's like, fine. Not distracting at all. Okay, so that happens with soap. Laundry detergent has sodium carbonate in it, which is also called washing soda. And the carbonate ions in that will precipitate magnesium and calcium. We just learned from that list that calcium carbonate and magnesium carbonate are insoluble. So these form solids, and then they are not available to make bathtub ring with the soap. So a precipitation reaction is a reaction in which a precipitate forms. Typically we're mixing two aqueous solutions. You pour them together and almost like magic a solid forms. So here we have an illustration of that happening. Two things that look like water, we pour them together and we've got this cloudy yellow stuff that forms. Now we saw precipitates happen when we did experiment 2. We poured stuff together and solids appeared. That's a precipitation reaction. So what we have here is we have potassium iodide, which from our solubility rules we know is soluble, and we have lead 2 nitrate, which is also soluble. So I think of these as being people going to a party. So the metals are masculine, so potassium is the guy and iodide is the girl. And here, lead is the guy and nitrate's the girl. And they're going to this party. The party's happening in the Erlenmeyer flask. They're going to the party and they're with each other, but they're not with each other, right? They're together, but they're not a couple. So they go to this party and they mingle, right? That's what you do. You go around, you meet people. Well, what happens is that lead meets iodide, and there is a major attraction between these two, right? They're like stuck together. You don't see them separated again at the party. In fact, maybe you don't even see them anymore because they went out to the back porch and they found a couch. And they're out there necking, right? And just completely ignoring everybody else. They've precipitated to the bottom of the beaker. They're stuck on each other. And what happens to potassium and nitrate? They're just hanging out at the party, mingling. They didn't get involved in a relationship. They didn't have chemistry with someone. Lead and iodide had a chemical reaction. That's what's happening in this precipitation reaction. So we need to learn how to predict the products of precipitation reactions. Waiting for screen. So here are our original solutions, potassium and iodide, and they separate from each other because they're soluble and they're floating around in the water. And here's lead and there's iodide. And when we put these two together, there are two possible products that can form. We know that potassium and iodide are not going to form a solid, because if they did, they wouldn't form this solution, they wouldn't be there. And lead and nitrate are not going to form a solid. What we're going to do is we're going to swap the partners and see if any chemistry happens. So potassium came in with iodide. We're going to see what happens when potassium meets nitrate. Lead came in with nitrate, but we're going to see what happens when he meets iodide. So we swap the partners, and then we look at the two possibilities, and we apply the solubility rules. And so potassium's in that first row. Everything with potassium is soluble. That's not going to form a solid. Lead, iodide. Well, we find iodide in the upper portion. Iodide compounds are generally soluble except with lead, so there's our solid. Precipitation does not always happen when you mix two aqueous solutions. Just like you could have a party and nobody gets into a serious relationship, right? Y'all got together, you had a lot of fun, and then you go your separate ways. Here we got potassium iodide and sodium chloride. So there's potassium iodide again, coming in and mingling with sodium chloride. But there's no major attraction because the possible products here are all soluble. The possible products are that one, potassium chloride. All potassium compounds are soluble. Or sodium iodide. All sodium compounds are soluble. Sodium, potassium, lithium, and ammonium, in my analogy, in my chemistry land, they are all masculine, and these are guys that do not make commitments with anybody, okay? They do not form precipitates. And then kind of at the other end, you've got phosphate and carbonate, and I guess those are women because they're anions, and they will form a precipitate with almost anybody except those guys who won't form commitments with anybody. It's a very strange analogy that's developed over the years. Here are a list of instructions for writing precipitation reaction equations. So you start with the formulas for the reactants, and then you swap the partners to predict the products. You refer to solubility rules to determine if there are any of them that are insoluble. If all of the possible products are soluble, you have no reaction. So you just write no reaction. If one or both are insoluble, then you have to finish off the equation and balance it. So let's do an example. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. So here we're not even given the formulas, we're given the names. So in order to write the formulas for ionic compounds, you need to write the formulas for the ions first. So we've got ammonium chloride. So ammonium is NH4+, because you memorize it. And chloride is Cl-. And so then we can put those two together to form ammonium chloride, NH4Cl, and the state symbol for that would be aqueous. This question doesn't specifically say it, but generally it's talking about mixing two solutions. We could also write aqueous because we know that ammonium compounds are soluble. And then the other one is going to be iron 3 nitrate. So iron 3 is Fe3+, nitrate is NO3-. So when I put those two together, I've got 1 iron and 3 nitrates, and that's also going to be a soluble compound. So the question is, what happens when these two solutions mix? So what we're going to do, I've already written out the formulas for the ions. I'm just going to swap the partners and see what happens. So iron's going to go with chloride and ammonium is going to go with nitrate. The attractive forces here are based on electrical charges. You have to put a positive with a negative. Chloride and nitrate are never going to be attracted to each other. It's the same electrical charge repels, always. So we're putting ammonium with nitrate. So we can go over here and write those together. And you always write the cation first. It's always the guy first and then the girl. And then we're going to have iron with chloride. Now, to potentially save yourself a little time, you can identify, is this soluble or not, before you start finishing off the equation. Ammonium and nitrate, is that soluble or insoluble in water? It's soluble, because all ammonium compounds are soluble. So this one's going to be aqueous, soluble. What about Fe and Cl? Well, and chloride is in the mostly soluble part of the table, and the exceptions were lead, silver, and mercury. Iron is not one of the exceptions. So that means that this is also a soluble compound. They're both soluble. Do we have a chemical reaction? Nope. No reaction. And sometimes we get even lazier and just write capital N, capital R, no reaction. Has something changed? Yes. We have mixed these things together. There's a physical change of mixing. There is no chemical reaction. Just mixing. Any questions? Yeah.
So there would be a reaction if one of them became a solid?
Yes. Yep. Okay, let's do another one. Here we got sodium hydroxide and copper 2 bromide. So sodium Na plus, hydroxides OH minus. Put those two together, NaOH. All sodium compounds are soluble, so there we go. And we've got copper 2 bromide. So copper 2 is Cu2 plus, and bromide is Br minus. And I look at the charges, and this is going to be CuBr2. Bromide compounds are soluble except for silver, mercury, and lead. This one's soluble. And then to predict the products, I'm going to swap partners. I'm going to put sodium with bromide and hydroxide with the copper. And it doesn't matter which one you put first in terms of, do I put the copper and the hydroxide first, or do I put the sodium and the bromide first? It's like adding, 2 plus 3 is 5, and 3 plus 2 is also 5. But we always put the sodium, the positive ion first. So sodium with bromide and copper 2 with hydroxide. And then let's ask ourselves, is this combination soluble? Yeah, all sodium compounds are soluble. So I'll write AQ here to remind myself of that. Copper 2 and hydroxide. No, because as you go through the table, hydroxide is in the bottom half. Hydroxides are generally insoluble, except calcium, barium, and strontium are slightly soluble. This isn't one of the exceptions, so this is going to form a solid. Now we think, dang, I have to finish this. I've got a solid, so there is a reaction. So I've got all the pieces I need to write the rest of this. So sodium and bromide, one of each. The copper will need 2 hydroxides, and then the state symbol is S for solid. And now I need to balance it. See, this hydroxide stayed together as a single ion, right? I had hydroxide here, and I've got hydroxide over there, so I can balance it as a unit. Here I've got 2 hydroxides. In the reactants, I only have 1. So if I put a coefficient of 2 in front of sodium hydroxide, that gives me 2 hydroxides on each side. And then here I've got Br2. I've got 2 bromines there and only 1 over here. So if I put a 2 there, so now I've got 2 sodiums, and I just fixed that one, 2 sodiums, the 2 bromides, the 2 bromides, 1 copper, 2 hydroxides, and 2 hydroxides. There's my balanced chemical equation. Any questions?